Hello everyone, welcome to the Electromagnetic Spectrum Lab channel. In this video I want to talk about some optics principles such as S and P-polarization of light, Fresnel Equations, and Brewster's law. At first, the plane of incidence should be expressed. The plane of incidence, or in brief PY, is defined as the plane containing the incident wave vector and the normal to the surface on which the incident wave strikes. Now we can define the S and P polarization of light. S-polarized light refers to the polarization component of an electromagnetic wave perpendicular to the PY. And for P-polarized light, the electromagnetic wave has a component parallel to the PY. Both of them are shown in this figure. The understanding of S and P polarization is crucial in many optical applications, such as designing polarizers, optical coatings, and laser systems. The concept of S and P polarization is relevant only for oblique incidence, no normal, because in normal incidence, the PY is undefined. When the light hits the surface, there is no specific orientation related to the PY, as all directions perpendicular to the propagation are equivalent. When light encounters the boundary between two media, the behavior of S and P polarized light can differ significantly due to the boundary conditions at the interface. The Fresnel equations can describe how S and P polarized light are reflected and transmitted at an interface. The Fresnel equations are obtained by these relations for S and P polarization of light. The media are assumed to be linear, homogeneous, and isotropic with refractive indices N1 and N2, permittivity epsilon1 and epsilon2, and permeability μ1 and μ2. Theta I is the incident angle and also the electric field of incident, reflected, and refractive waves are labeled as EI, ER, and ET respectively. In this slide, I plot the amplitude of reflected S and P polarized waves for a non-magnetic media versus different incident angles in two modes, internal reflection and external reflection. In both internal and external reflection modes, we can observe there is an angle at which the P-polarized reflected wave becomes zero. This angle is called Brewster's angle. This phenomenon occurs only for P-polarized light in the case of non-magnetic media. Also in internal reflection mode, it can be observed that in a critical angle for both polarizations, the reflection increases to unity, and after that it remains at this value, which corresponds to the total internal reflection. As in the previous slide, the calculations are repeated for magnetic media. In this case, Brewster's phenomenon occurred only for S-polarized light instead of P-polarization. As explained before, Brewster's angle is defined as the incidence angle at which the light is perfectly transmitted through the surface without any reflection. For non-magnetic media, Brewster's angle is observed only for P-polarized light, and for magnetic media, just for S-polarization, there is an angle at which the reflectance becomes zero. In general, the Brewster's angle can be calculated by this equation. In review, I introduced the S and P polarization of light and the Fresnel equations formulations, and also showed some examples of reflected wave behavior in the non-magnetic and magnetic media associated with the definition of Brewster's angle. I hope this video can be helpful for you, and I would be grateful if you could subscribe to my channel and like and comment on the videos. Good luck and have a nice time.